Okay, so I mentioned at the end of the previous video about how sometimes the map units weren't necessarily 100% accurate, and then it was more of a relative distance that you could measure. One of the reasons for this is because as you increase the distance between two genes, these mapping estimates are just going to become more and more inaccurate. And one of the reasons for this is because you can start to see things like this two-strand double exchange. Okay, so if you had a single crossing over event, it might be easy to see that when you're looking at the offspring. But if you've got this double crossover, it's actually very difficult to determine that you have it. And the reason why is because in these offspring, if these genes are far enough apart, you're not going to be able to notice that you actually had this recombination event happening. And so what you see as you increase the map distance between two different genes, so as this theoretical goes up, it's pretty linear. As the actual goes up, you can see that it's not going to be quite as accurate. So one of the ways we can measure this is through something called interference. And interference basically reduces the number, if there's genes are too close together, whether it's physical through that they're just too close or too far apart, there can also be what we call interference. So interference, what it's going to do is reduce the expected number of multiple crossovers when you have maybe a crossover event in one region of the chromosome inhibiting a second event that also happens to be nearby. You can have complete interference. That would be when you had no double crossovers occur where you would expect those to happen. You can call something a positive interference if you have fewer double crossover events than you expect. And you call something a negative interference if you have more double crossover events than expected would occur. Maybe you have a region of the chromosome that has very high frequency of recombination, and so the number of crossover events that you have might be higher than you would expect. So when these two genes are close together, simply the physical distance between those genes means that you're going to have positive interference happening, and the accuracy of mapping can be pretty high. However, as the distance between them increases, as we just talked about, the interference is going to decrease, and the accuracy of mapping those two genes is going to thus subsequently decrease as well. You can actually calculate some of these numbers. Okay, so let's just do an example. So let's just say in an example you've got 7.8% of the offspring would be a double crossover event. However, you expected to get it 9.7% double crossover rate. Okay, and this happens a lot. A lot of times in these mapping experiments, your actual observed double crossover rate is going to be less than the expected number of double crossovers. And so because this was less than your expected, interference was probably responsible for this reduction. So it's pretty simple to calculate. If you divide these, first convert these two percentages to a decimal number, and you divide them, you can get another number. Okay? If you subtract that number from 1, it will give you another number that you can convert to a percentage. In this case, you would expect you had 19.6 fewer double crossovers than expected. Because it's fewer crossovers than double crossovers than you expected, this is an example of positive interference. If it's a number here that's going to be positive, okay, it's literally positive interference. If that number is negative, say this is bigger than 1, then that would be an example of negative interference. Okay? In this case, you have more crossovers than you would expect for a particular event to happen. So one of the forefathers of modern genetics is Mendel, right? Mendel was pretty lucky because he never ran into these effects of linkage when he was conducting his experiments. He might have gotten vastly different percentages when he was looking at these potential crossing over, if he had to deal with potential crossing over events that were happening. Many people think this is because he had 7 genes, pea plant only has 7 chromosomes, hey, 1 per chromosome. That actually wasn't the case. Some of the genes he looked at were indeed on the same chromosome. But for whatever reasons, he actually did not run into the effects of linkage when he was conducting his experiments. If he had, we might not have been as far along in genetics at the time at all.